Okay then, the purpose of this short clip is to show you how to apply Dijkstra's algorithm to a network, and the purpose of Dijkstra's algorithm is to be able to find the shortest path from one node in the network to all of the other nodes. So this is a typical small pencil and paper problem to which we could apply Dijkstra's algorithm, and what we're going to be doing here is to try and find the shortest distance between node A and node G. Now at this stage we don't know what the shortest path is between A and G. It might potentially be that. It might potentially be that. We don't know at this stage. So that's why we're going to apply Dijkstra's algorithm. Now, if you end up doing a problem like this in a public exam, you probably won't be given a grid like this. You'll probably actually be given one with boxes on in which to jot your workings. Now, this is a typical type of exam template, and we're going to start at node A. Now, this is pretty straightforward. The distance from node A to node A is 0. And so that's the temporary workings, that box, and the permanent distance can be 0, and that box there, the 1, is the order that it became permanent in. So that's pretty straightforward. Now the first thing we do, from node A, we look at the distances to the nodes that connect it. So that one's 3, that one's 8, and this one's 12. And I put the workings down the bottom because there are temporary workings. Now what we do is we choose the shortest. So the shortest in this one here is obviously the 3. So we make node B permanent, so the distance from A is 3, and that became the second one we made permanent. Now the next step is we've made B permanent, so we look from B, we go up to E. Now the distance of E from A is 5. Now where does that come from? Well, it comes from that 3 there and that 2. And then we go from B, we're interested in what's the shortest path down to C. Now that's interesting because if we go from A to C but via B, it's 3 and it's 4, which is 7, which is actually shorter than the 8, so we cross out the 8, we put the 7. Now what we're interested in is what's the smallest temporary label. So we've got a 5, we've got a 7, we've got a 12, and we're always interested in the smallest, so it's the 5. So we make E permanent with a permanent label of 5, and that's the third one that became permanent. Now we repeat the process. So we've made E permanent, okay? So we go from E, and from E we can go to G. So the distance from A to G via E is 5 add 14, which is 19. Now we can also go from E to C. Now this is interesting because we've got the 5 and that distance there is 1, so we can cross out the 7 and make that temporary label a 6. And then the process is exactly the same as before. We say, well, what's the smallest number? So we've got a 19, we've got a 6, we've got a 12. 6 is obviously the smallest, so the distance from A to C is 6, and that was the fourth one that became permanent. And now the process just repeats over again. So C was permanent, and that's distance 6, so if we go from C, we can go down to D. Now 6 add 3 is 9, so we can update that, and we can also go from C to F, so that's 6 add 9, which is 15. And now exactly the same as before, we look at the temporary labels. We've got a 19, we've got a 15, we've got a 9, we make the smallest one permanent. So node D has a distance from A to D of 9, and that was the 5th one that became permanent. And now, exactly the same as before, we repeat. Now obviously, in terms of from D, well, A's been used, so we did that, so we can only go to F, which I'll do along the bottom. So 9 plus 5 is 14, that's less than the 15. We update. Now I look again at all my temporary labels, and I've got a 14, I've got a 19, I make the smallest one permanent, so that's 14, and that one, there's a 6th one that became permanent. And now exactly the same as before. Well, I'm at F, I can't go back that way because I've already made it permanent, so it only leaves me to go there. Now 14 and 3 is 17, okay, which is smaller than the 19, and then that is the final one that I make permanent. So the route from A to G is, well, sorry, the distance from A to G is 17, and that was the 7th node that was made permanent. Now the very final thing we usually have to do in an exam is actually just state the route that gave us that shortest 17 from A to G. Now we can literally backtrack and say, well, where does the 17 come from? Now if we follow it through, starting at A, we went 3 there, we went 2 there, we went 1 there, we went 3 there, we went 5 there, and we went 3 there, which finished up with our 17. So we just state it. So it was A to B to E to C to D to F to G, and that had a weight of 17. And that's essentially how you apply Dijkstra's algorithm to a simple network like this one. Finally, and as always, I hope you found this clip useful. If there's any queries, please don't hesitate to get in touch via email. Thank you very much, and thank you for listening.